Hey everyone, and welcome to the Explainer. So if you've got a math exam coming up, or you just want to completely master the fundamentals of mathematical logic, you are absolutely in the right place. Set theory isn't just for passing tests, right? It's literally the invisible logic running our databases, search engines, and basically all of computer science. Today, we're running a full-on exam prep bootcamp on set theory. I'm going to be your enthusiastic tutor, guiding you through the source material, and together we're going to build a rock-solid understanding of these concepts so you can totally crush your next test. All right, here's our game plan for today's master class. First, the foundation of sets. Second, empty and singleton sets. Third, finite versus infinite sets. Fourth, visualizing with Venn diagrams. Fifth, solving set theory problems. And finally, comparing infinite sets. Let's just jump right in. Okay, let's dive into section 1, the foundation of sets, building the mathematical blocks. Before we start throwing any wild equations your way, let me pose this foundational question directly to you. What exactly makes a set? Seriously, think about it for a second. If I tell you to group some things together, what mathematical rule actually makes that group an official textbook set? Well, here is the absolute golden rule straight from our sources. A set is a well-defined collection of distinct objects where contents can be clearly determined without ambiguity. Now, the absolute crucial phrase here is well-defined. It means anyone, anywhere in the world, looking at the rule for your set would pick the exact same objects to go inside it. No guessing allowed. To really wrap our heads around this, let's look at what actually fails the test. These collections are absolutely not well-defined sets. The collection of cute animals, the collection of best math teachers, or the collection of difficult problems. I mean, we can all agree puppies are incredibly cute, but what makes an animal cute is totally a matter of personal opinion. Because terms like cute, best, and difficult are subjective, they completely fail the mathematical test for being well-defined. Moving right along to section 2, empty and singleton sets, the smallest boundaries. Now we're looking at the absolute smallest sets imaginable. It's a brilliant contrast between having literally nothing and having exactly one item. We have the empty set, which contains no elements at all. Its cardinality, which by the way is just the fancy math word for the total number of items inside, is exactly 0. Then contrasted with that, we have the singleton set, sometimes called a unit set. It contains exactly one element, giving it a cardinality of exactly 1. Let's walk through some concrete examples so you can spot these from a mile away on test day. An empty set would be something like months with 40 days or odd numbers divisible by 2. I mean, those just don't exist, right? Now, a singleton set would be the even prime numbers, which is literally just the number 2, or vowels in the word math, which is just the letter A, just one single item in each. Okay, I want you to think about the number 0 for a second. This is a classic exam trap. You might think an empty set, just because it has absolutely nothing in it, is somehow undefined or infinite. But no way, because an empty set has a specific countable number of elements, exactly 0, it is officially considered a finite set. Seriously, do not let your professor trick you with that on your next test. All right, we are scaling up. Section 3, finite versus infinite sets, breaking the boundaries. So what's the core difference here? Well, for finite sets, the process of counting elements will eventually stop. You might be counting for a very, very long time, but you will eventually hit an endpoint. Versus infinite sets, where the elements are uncountable. The list literally goes on forever, and you can never ever finish counting them, no matter how much free time you have. I really want to emphasize this exact phrase from our sources regarding infinite sets. The list of its elements goes on forever. The prime example of this is the set of all natural numbers, 1, 2, 3, 4, and so on. You can always just add one more, right? So there is no end. In set notation, we usually represent this never-ending sequence with an ellipsis. Those 3 little dots at the end of our roster list. But hey, here is a super surprising fact to really test your understanding. The set of all sand grains on Earth is a finite set. Crazy, right? Why? Because just because a number is astronomically huge and practically impossible for a human to actually count, doesn't mean it's infinite in a mathematical sense. There is a fixed, definite, physical boundary to the amount of sand on Earth. It eventually stops. So, yep, it's finite. Section 4. Visualizing with Venn diagrams, drawing the logic. Consider this concept your ultimate exam cheat sheet.
John then gave us a brilliant way to map relationships between sets, translating visual shading directly into mathematical operations. Think of the union, represented by that U shape. When both entire circles are shaded, it means everything in set A, set B, or both. For an intersection, the upside-down U, only the overlapping middle part is shaded, meaning only the specific elements that exist in both sets simultaneously. And if two sets are disjoint, well, their intersection is the empty set. Visually, they're just two completely separate non-touching circles. Definitely memorize these visual translations.
All right, time to put these building blocks into practice. Section 5, Solving Set Theory Problems, Exam Practice. Here's a question straight out of the test bank. Find the cardinality of the set of all months beginning with M. I want you to challenge yourself right now. How would you mentally solve and structure the answer to this? Think about the distinct steps you'd take to ensure you get absolutely full credit. Okay, here is the exact logical flow that is going to guarantee you those full marks. Step 1, identify the elements and write them out in roster form. Let's call the set S. So S equals the set containing March and May. Step 2, count the distinct objects. We have 1, 2 items. Step 3, state the cardinality. Using the absolute value bars around the S, we write cardinality of S equals 2. Breaking it down step by step exactly like this leaves absolutely no room for error. And finally, we've reached the absolute climax of our explainer. Section 6, Comparing Infinite Sets, the advanced climax.
So, we know we can count finite sets to compare them, right? But how in the world do you compare the size of sets that literally never end? Well, mathematicians use a really clever technique called one-to-one correspondence. The definition is pairing every element from one set with a unique element from another set with absolutely no leftovers. If you can perfectly pair them up endlessly, they actually have the same cardinality or size. The really crucial point is how this pairing works in practice. The set of all even numbers, 2, 4, 6, 8, and so on, pairs perfectly with the set of all natural numbers, 1, 2, 3, 4. The 1 pairs with 2, the 2 with 4, the 3 with 6. Now, what's truly mind-bending about this is that even numbers are just a fraction of all natural numbers. I mean, they literally skip every single odd number. Yet, because this pairing goes on forever without missing a single beat, they actually have the exact same infinite cardinality. Which brings us to a truly mind-bending final thought. If even numbers pair perfectly with all natural numbers, despite seemingly being a much, much smaller group, are some infinities the exact same size? And if so, does that mean there are other infinities out there that are actually entirely different sizes? I'll let your mind chew on that one for a bit. Keep practicing these concepts, trust the structured logic we went over today, and you are going to absolutely crush your exam. Thanks so much for joining me on this explainer.